Hi everybody, my name is Moshe Zadka, my website is cobodism.com, and today I want to talk to you about Hamcrest, how to check exactly what you want to check. I would want to start with an acknowledgement of country. I live in Belmont, in San Francisco Bay Area Peninsula, which is the ancestral homeland of the Ramaytush Ohlone people. So, before we talk about how to check stuff, let's think about the context. What is a unit test? And that's a very, at times, charged debate. What is or is not a real unit test? So let's talk about the things that people think of when they hear the word unit test. So one feature that is very common in unit tests is isolation. They work isolated from the environment, isolated from the operating system, isolated from the network, isolated from other stuff. They're fast, right? You expect that your unit tests will finish quickly. And weirdly, this is the least useful thing, but is the reason that unit tests are named that, because they test a unit. There is a small system under test. There's a small part of the code that actually has to function correctly for the test to pass. And often that is the least useful feature of unit tests, so some people care a lot about it. And I'm going to talk about how to write unit tests better, and these are the things that make unit tests unit tests. But hopefully we all have them and we all want them to pass. So let's think about how they tell us stuff about our code. So there are many ways to write Python unit tests. You have first the runner. The runner is something like nose or PyTest or Virtue that will look for your tests and actually run them. Now, when you write your unit test, you have to write your test cases somehow. Some things like nose or PyTest will support just plain functions as test cases, or maybe just classes that look exactly the way. Some things lean more on having some support inside the code for unit tests, like inheriting from unit test case, or other test cases like test tools, test case. And finally, in your unit test, you want to say what you expect to be true. Yes, just running the functions and checking that they don't raise exceptions is a little bit useful because they're not raising an exception. Is hooray! Probably your code is not, complete garbage. You probably didn't just bang on the keyboard and then checked it in. But that's very little, right? Usually you want to say, and that function returned 3, or at least that function returned something that is greater than 5, or whatever. You want to assert things about the values coming out of the unit test. I'm sorry. And we call those assertions because we assert that these things should be true. There's many ways to assert depending on exactly how you write your unit tests. For example, PyTest uses assert rewriting. So when it is the assert the assert statement, it rewrites the bytecode to produce bytecode that will actually give you useful data about the assertion. Unit test case has assert underscore a whole bunch of things like assert equals, assert greater than, assert contains, a whole bunch of stuff. Then there's like test tools, test case has assert that is a little bit more flexible. And these are all the things you need. You need the way to run them, you need a way to write, you need a way to run them, you need a way to write the unit test, and you need a way inside the unit test to say what you expect to be true. A lot of these solutions, as you saw, showed up in more than one place in my anatomy because they're all in one. PyTest, test tools, unit tests basically expect to own all 3 parts, which is sometimes useful, but sometimes you want something, more a-la-carte, where you can pick and choose your bits and pieces. So you can choose an a-la-carte runner, like say nose or Virtue, and the only library I'm familiar with which gives you a-la-carte assertions is Hamcrest. So what Hamcrest does, it doesn't care about test cases, it doesn't care about unit tests, it doesn't care about how you run them. All it cares is how to say what you expect to be true. And because it focuses only on that goal, only on the goal of how to allow you to express what your expectations are, it does a pretty good job at allowing you to express what your expectations are. And I'm going to dive into how it does that and how it can make your unit tests more precise. And I use the term precise, but I use it kind of imprecisely. What does it mean for a unit test to be precise or to be good? So how do you measure the quality of a unit test? If I claim that this might make your unit test better, we need some metrics, some value to assign to unit test. What does it mean that a unit test is better than another? So there's two ways for a unit test to be bad. One is false alarm. And depending on which field you come from, there's a lot of other names. I find at least false alarm, you cannot mistake it. You know what it is. It is an alarm that is raised incorrectly. So some people call it false positive. Then you have to remember that positive means that it fires, not that it's good. But false positive is a very common term of the art. And even more thing that you have to just memorize is type 1 error, as opposed to type 2 error, which we'll talk to in a while. But you have to just remember false alarm is type 1. There's no good mnemonic, except for the mnemonic that I'm going to give you now, which is, if you remember the story about the boy who cried wolf, the first thing he does is cries wolf when there is no wolf, and that's a type 1 error. And that's asserting things that don't have to be true, right? Like you say that there's a bug, you say there's a wolf coming, you say there's a monster, you raise an issue, you mark the PR red, and there wasn't a problem. The PR was fine, the test misfired. So that's bad because you're wasting someone's time fixing a test, while if there was no test, they would not have to do any more work. Their code was perfectly fine. So this is not a good unit test. It does not give us value. The other kind of unit test failure that can happen is missing alarm. And again, depending on your field of studies, there are different terms of art here. You can call it false negative or type 2 error, which, if you remember the mnemonic I just taught him, the second part of the boy who cried wolf story is when the boy cries wolf when there's actually a wolf, but nobody believes him. So the alarm he raises is not useful. That's a type 2 error, that like there's no alarm, that nobody is looking for the wolf. But the wolf is there and very dangerous. And the bug in your code is just about to be checked into production and harm potentially a lot of people who use that. So that's not good. And basically, you can think of it as not asserting things that have to be true. If a function always has to return 3 when it gets 2, and returns 4 when it gets 2, we could have asserted it. We could have given it 2, checked that it gave 3, said it has to be 3. Not it has to be greater than 2, right? Because that would accept 4. But if we expect it always to be 3, or if we expect it always to be between 3 and 3.5, we can say it has to be between 3 and 3.5. And if we didn't do that, if we didn't make a unit test strict enough, then we have potentially let a bug through a unit test. And since they have one job, right, which is to prevent bugs. If I didn't care about bugs going into production, I wouldn't bother writing the unit tests, right? The only reason to write a unit test is to prevent the bug from going into production. So they've, like the alarm that doesn't go off when a burglar hits the house, right? It failed in its only job, which is to alarm when something bad happens. So that's bad. And I noticed that it's kind of weird because you can trade off between these two badnesses, right? If you assert very, very, very specific things, then you let very few bugs through, but you'll also fire on everything. And you can think of it as like the extreme case is assert 1 equals 0. I can guarantee you that no bug is creeping past that unit test system. However, there are also a lot of non-bugs that will not creep through these unit test systems, all of them. So that's not useful. And the other extreme case is just not having unit tests. And I can assure you there will not be any false alarms. But on the other hand, like, you're not going to catch any bugs in this unit test because they always pass. So when we talk about the quality, right, if we only concentrate on one, then we can just go the other extreme. We have to somehow say we care about both to measure the quality of a unit test. And luckily, there are already metrics that measure while trading off missing alarms and false alarms, or type 1 and type 2 errors. And one popular one comes from the field of artificial intelligence and classification, where it's very similar. You want to say what you classify as, in the category, and what you classify not the category, and what is true and what is false. There you have an equivalent problem to solve, and they came up with something called the the F1 measure, the F1 score, and the generalization is the F beta score. So let's talk about the F beta score. And so this is how we'll measure the value of a unit test suite. So you get beta, and beta is the trade-off term. If beta was infinity, then I care ultimately about missing alarms, but I don't care at all about false alarms, and I might as well just do assert 1 equals 0. And if beta was 0, I don't care at all about missing alarms, but I care about false alarms, in which case I just don't write any unit tests. So clearly, infinity and 0 are bad values. 1 says that I care about them equally. So a missing alarm is just as bad as a false alarm. There's other common values. 2 means that you care about missing alarms twice as much, false alarms. And what I want to say really is that, like, almost no matter what's the beta, you want to see how you can improve. Now, if you're given a specific beta, you have a specific goal. But there are many things that can just improve the F score for all possible betas except for 0 and infinity. And we should probably concentrate on those and not concentrate too much about how to trade off between them. But it is important to think that if you really want to measure the quality of your unit test suites, you should figure out how those two values matter for your development team and where would you put the beta. And the actual formula is not super interesting. This is a formula. You can just copy it off of Wikipedia, or you can, but then it's like mathematical notation. I transformed it into Python here. But that's a formula, right? Like you feed in the number of true alarms, the number of false alarms, the number of missing alarms. It's very important to count true alarms correctly. If you only count true alarms in CI, you're probably miscounting them because a lot of true alarms don't get to CI. They will get cut when the developer runs, say, something like talks on the local machine. So if you actually want to count, you should be very, very careful that you're counting the correct data. False alarms are a bit easier because false alarm you'll see in CI because the test has to change. So any diff that touches a test that didn't have to change, that the overall interface didn't change, that's you can think of that as a false alarm. And a missing alarm is also kind of hard to measure, but you can think of any time you get a bug cut past the unit test suite, you can count it as a missing alarm. So it's possible to actually have this measurement as a development organization or a development team and see where you are on the F score. And, like that might matter for your KPI. And I guess the reason I'm concentrating too much on that because I'm trying to talk about how to make unit tests better with Hamcrest assertion. And I want to make sure that I commit to a specific standard of better so I can't equivocate. This is better. Better means that at least for a lot of betas, and again, like you'll have to think about your beta when you actually write assertions, but whatever your beta is, Hamcrest will let you improve your F score. And usually you can think of just F1 score if beta is 1. And that's probably like, unless you are have very, very specific constraint, that's probably what you should be aiming for at the first approximation. So I wrote a little decorator called show assert because one of the cool things about Hamcrest is because it doesn't depend on unit tests, I can show well, most of the time you write these assertions in unit tests. My talk will not show unit tests because this is not talk about unit tests, this is about assertions in unit tests. So I wrote a little context manager called showAssert that shows you the assertion errors and kind of formats them nicely. And specifically, it's like highly optimized for slide decks. So it does like weird formatting so that it will fit on a slide, because sometimes you have to. Anyway, the most simple assert is equal, right? We can assert that 1 is equal to 2 and 1 is not 2, and properly Hamcrest will yell at us that it's expected 2, and it was 1. And I noticed that this is one of the coolest things about Hamcrest, and we'll see how it matters more in progress. There's asymmetry. Is what you got, which is a specific value. You cannot argue with that, right? You might not like it, but that's definitely what you got. You call that function with parameters, and it returns 1. That's a specific value. However, there's the expectations. The expectation is not necessarily specific, right? Like in this case, it is specific. I want it to be exactly 2. But the expectation can be 2 or 3 are okay, right? If you wrote it in PyTest, you probably write assert 1 equals 2 or equals 3, right? Or, maybe it's close to, right? There's like all kinds of things that you can say that are not necessarily specific, that are constraints, but are not complete constraints. In this case, it is a complete constraint, but there's a symmetry. There's what we got, and then what we say about it. And a lot of assertion libraries make them equivalent, right? If you think about assert in PyTest, for example, right? Assert X in Y. Which one is what you got from the test, and which one is the thing that you're checking against? It's symmetric, right? But there's really 2 kinds of assert X in Y. There's I got X from the test and it has to be in Y, and I got Y from the test and I know that it has to contain X. And those are different things to assert, and you probably want to grade different errors on them. So in PyTest, I expected 2, and you gave me 1, and 1 is not equal to 2, and that's not good. So like I said, containment is kind of interesting, right? I want to say that 1, 2, 3 has an item 5, and it does not. So Hamcrest is annoyed and said, I expected a sequence containing 5, and you gave me 1, 2, 3 that does not have 5 in it. So, sad. Then you can also do assertion that one of 2 things is true. And in this case, I'm choosing equal to 2 or 0, but I can choose any 2 assertion and say this has to be true. I'm not sure which one has to be true. For example, think of something that might or might not pass through a cache, or something that might be dependent on a random value, or a value that's very hard to predict. Whichever is the case, you can still say definitely one of those 2 has to be true about it. Then you can say, I want all of these to be true. And I notice that in this case, it's not that 1 and 4 will have any specific relation. 1 may be before 4, 4 may be before 1. In this case, there's just no 4. And you notice that it clearly tells you which part of the assertion was false. It expected both of these things to be true, and specifically a sequence containing 4 was not a sequence containing 4, and that's very unfortunate, and Hamcrest will tell us exactly the problem. Now, the things are composable. So I can say that this sequence, which is a sequence of sequences, has item that has an item that has 5. And Hamcrest will correctly says, I expect a sequence containing 5, and you gave me a sequence that all sequences do not have 5. So this does not pass the master. You can also say exactly what things there are. So for example, I expected a sequence containing 1, 2, and 4, but item 2 was 3. It tells you exactly which thing got wrong. Or you can say, I'm not really sure what's the order of things in that list, but definitely all these things. So I expect 1, 2, and 3 to contain in any order 4, 3, 1, but that means that 2 is not matched, meaning that I expected only 4, 3, and 1, and I didn't expect 2, so I'm very sad. And Hamcrest is commiserating with me, well, telling me exactly what went wrong. But one of the cool things of composability is that you can literally write your own Boolean expression. So you can write an exclusive OR. So let's write a little exclusive OR. It's kind of a fun exercise, right? Where I say exactly one of condition 1 and condition 2 have to be true, right? They can't both be true at the same time. So I just say that both condition 1 and condition 2, one of them has to be true, and one of them has to be false. And I can just compose it with not. So I literally have the ability to write really, really complicated Boolean expressions. This is just like a fun example. And I can say assert that 1, 2, 3, exclusive OR has item 1, I hate item 2. And it tells me, well, like the first part worked, but 1, 2, 3 is a sequence containing 1, so it doesn't match not a sequence containing 1, or not a sequence containing 2, and sorry about that, your test did not pass. So this is, again, an example for like something very, very specific. The only thing I know is that it has to have 1 or 2, but not both. And that's very common, right? You might say, you know, only one of the things in this sequence should, you know, should be like, you know, kind of expensive, right? You can buy an expensive thing and a cheap thing, but not 2 cheap things or 2 expensive things. Right, so that's, you know, realistic in, again, depending on your exact flow. Let's talk about floating point numbers. So we assert that 0.1 plus 0.2 minus 0.1 minus 0.2, which looks like it should be 0, but it's not 0, because floating point numbers are weird. And but Hamcrest knows that they're weird, it expects it, so it gives us an assertion that it's close to. But I told it to be close to 1 and not close to 0, so it's almost 1 away. So even though it's a very, very small number, it's not 0. So if I had done equal to 0, it would fail, but equal to 0 is the right thing, or maybe I forgot to add another 1 here. But because floating point numbers are weird, you usually want to check that they're approximately equal to something, because it's very, very hard to constrain them to be equal to something exactly. And then you can do stuff like string contains in order, hello world I. So you notice that all the i's are after the world. So even though it looks like it should work, it doesn't, because the string has to contain them in order. And that's, you know, sometimes very important. For example, you can use it to check that some string manipulations are correct, and we'll talk about this a bit later. You can also check dictionaries. So you can say, I want value to be close to 0.5 to within 0.3, but of course 1 is a whole 0.5 away from 0.5, so it does not match. And Hamcrest correctly fails our assertions. By the way, all the assertions in this talk will fail, because I feel like this is like where the fun begins. Not in real life. In real life, it's probably not fun, but in the talk, the only fun we can have is if we let the assertions fail. So one really nice thing about Hamcrest is that it, you know, if none of the matches that currently exist satisfies you, you can write a custom matcher for any arbitrary condition. So let's first write a simple funny one, just to kind of get our feet wet. Let's check priority. This is not efficient. I did not have room here to write an efficient algorithm, but this is the obvious algorithm for checking priority. We just go over and check if any of the factors, and we say that we expect a prime number. There's no parameters here, because priority is just, we could have done like mutually prime, but I didn't want to do that. So is prime, return is prime. So this is very common, and let's see how we use it. we can assert that 6 is prime, and it tells if we accept a prime number, and we got 6. We could also have, like, worked a bit more and say what's the factorials, but I don't want to get too complicated. Let's do a more interesting, because when is this gonna come up? If you care about prime numbers, you probably already have great ways to work on that. Let's do something that matches whether a sequence has some items in this order, but you don't care about the other items. You just care that it has these items in that specific order. So let's see. So I couldn't write the whole class in one slide, so I'm going to have to do that so that we can build the class incrementally. So we build the class with a sequence of matches, and then I want to match the sequence one by one. So I take an iterator over the sequence, and whenever I match things, I move on to the next matcher. And if I run out of things to check, then I know that one of the matches didn't match, and otherwise I can return true. And when I describe, I just say there's a sequence containing thing, followed by thing, followed by thing, followed by thing, followed by, and then the last thing. So that's a description of the matcher itself. You can also, like I said, describe mismatches, but this is already getting pretty long. The last thing is you always want to make sure to do the wrap matches, and that allows people to do like sequence of 1 to 3 and not sequence of equal to 1, equal to 2, equal to 3, which gets a bit long. So this is a very common kind of quality of life enhancement to any common matches that check recursively matching. And let's see how we use it. So we want to check that 152 has items in order 1, 3, which it doesn't because it doesn't have a 3 at all. And it doesn't have items in order to 1 because it has a 2 and it has a 1, but by the time it got to 2, it already discarded the 1. And you know that this is a DQ. You can't access, you don't have random access to DQ. The only thing you can do is iteration, but because I built my stuff on the sequence interface, I just iterated over it. I can iterate over any sequence, so this just works. So the last cool thing I want to show is like a few kind of more realistic examples, slightly more realistic because it's pretty hard to show really realistic. But let's say that we want to check kind of complicated string output. So it tells greetings and the ultimate answer, and those things might change, right? Those things tend to change a lot, right? Like someone says, oh, like that you shouldn't say the ultimate answer, you should say the great answer, or something like that, right? Like, but I don't care about that, right? Like the strings are probably gonna be correct. What I care about is the details. Do I calculate the details correctly? And this is where a string contains in order just works great. So what I want to know, what I know is that I want the user. After that, it has to tell it the answer, and then it has to tell it the important concept. So here's how the function would work, right? Greetings Pyjamas, the ultimate answer is 42, and if you multiply by 10, you get the important concept of 420. And what I want to make sure that I have Pyjamas, I have 42, and I have 420. Those are the important things that I want to make sure that I calculate correctly. So we just do, we check when we greet someone, whether the output contains someone uppercase, and because we forgot the uppercase when we wrote the code, this will fail and say it didn't work. So this is an example for how it's really useful to show, especially if you do any string templating, this can come in really handy. And of course you can combine assertions, so you can say it has an item greater than 3 or it has an item less than 1. Of course it doesn't have any, so it fails. You can do pretty complicated things with data structures. So you can say the hello greeting has to end with exclamation mark, but the goodbye must not. And it says the value for hello didn't match. The value for goodbye was absolutely fine. So what are the takeaways? You should test what you're guaranteed to get. You should not test what you're not guaranteed to get. And Hamcrest can help you tell the difference, but it's not magic, and you still have to work. Thank you all for listening, and I hope that this will help you write better unit tests.